Welcome back. Let's talk about the definition of some of these asymptotics. Let's start with big O. All right, so the definition is as follows. So we have a couple of functions, f of n and g of n. We're going to say that f of n is big O of the function g of n if and only if the following inequality is true, right? That f of n is less than or equal to some constant multiple of g of n eventually. And by that, what we mean is for all n bigger than or equal to some point here, n naught. Okay? So what we're talking about is a couple of constants, right? So if we look at this, f of n and g of n are going to be given to us, and we're going to need to find these constants. So c and n naught. Right? So c is a real number, right? So it could be as small as 0.001. I mean, but it has to be. It has to be a real number, and it has to be positive. And n naught is also, well, it's not. It can be negative. N we're talking about is like the size of the input, right? So it can't be negative, and it's also an integer, right? So for example, you're talking about the size of your array, right? So it's an integer. And f of n and g of n are functions over non-negative integers, right? So we have non-negative inputs. And since we're typically talking about things like runtime, you have non-negative outputs as well, right? Now, if we were going to look at this sort of graphically, right? So here's my function f of n. And what I see here is that f of n is less than or equal to, right? It's less than this multiple of g of n, right? So there's some space between them here. All the time, well, maybe not all the time. Maybe when n is small, it's not true, but eventually once you hit to this point right here, n naught, then every point to the right of that, for any input that's bigger than n naught, then the runtime of n is going to be, or this function f of n is going to be less than this multiple of g of n. Okay. All right, so we're going to typically ask you to do proofs where you're going to have some functions and you're going to have to prove that something is big O of something else, right? So to do this, you're going to find two constants. So here's our definition right here. Again, there have to be two positive constants such that for all n that's at least n naught, this inequality is true here. Okay. So if I ask you, how do you prove that it's big O? The answer is that you have to give the two constants. All right. So let's take a look then at an example. All right. So this is an example on your quiz if you're doing this for class. First of all, I suppose I haven't given you any time, but you probably want to pause the video right now and go ahead and answer question 7a. I skipped over that kind of fast, but 7a is the question about the formal definition of big O. Okay. Once you've done that, we'll take a look at question 8. Okay. So question 8 is we have some function f of n. And the first thing that we're asking you to do is to find a simple g of n such that f of n is big O of g of n. All right, so we ask ourselves, f of n is big O of what? All right, so you find the g of n. You already know how to do this. This is the intuition, right? So a simple g of n that would work here, well, f of n, this function is big O of n, right? So that's our g of n. All right, so g of n equals n. Second thing we need to do is to prove it using the definition, right? So I need to find some constants such that this inequality is true, such that f of n, 4n plus 15, is less than or equal to some constant c times g of n. G of n is my n. So, and that has to be true for all n bigger than or equal to some point. In other words, at what point does it become true? Well, let's think about this here. N can be, so I have my n. The constant can be any constant, and I can pretty much get anything to work out. But let's start easy here, right? So what could you use? Let's think of some obvious numbers, right? So if this is 4, why not use 5, right? Is 4n plus 15 less than or equal to 5n? Generally, okay. I mean, it's pretty much true. Although if I were going to actually solve this inequality, right, bring the n over, so subtract 4n from each side, then I'd say, and I'll just rewrite this here, that it's true when n is at least 15. Well, great. So this is true for all n bigger than or equal to 15. I've just solved the problem. because I said that my function f of n is less than or equal to some constant multiple, so c equals 5, right, of g of n for all n bigger than or equal to this n naught, which is n bigger than or equal to 15, okay? And I have two constants here that work. Well, that's good, okay? Did y'all use that? Well, there's some other obvious ones, right? What about if you had 4n plus 15 less than or equal to, all right, for all n bigger than or equal to what? All right, so let's try this. What if I added the coefficients, all right? 4 plus 15 is 19. Is 4n plus 15 less than or equal to 19n? Well, that's a really easy thing to show. 4n plus 15 is certainly less than or equal to 4n, that should be a 4n plus 15n, which equals 19n. All right, so that inequality is true. Well, when is this true? Well, when is 15 less than or equal to 15n? Well, if n is at least 1. Okay, so could you have proven it by using c equals 19 and n naught equals 1? Sure, okay? You just have to give some constant. It says there exists, right? So you have to show ones, okay? Pick easy ones so that you can easily show me that this inequality is true, okay? Make your life easy, okay? Let's see. Let's actually think for a second here. So big O, that works. Actually, let's go on to another one, and then I'll come back and talk about this soon. Okay. So our second example. So this is question 9 on your quiz. So we have something slightly different. So now f of n is equal to n plus sine of n. You want to find out that's big O of what? So what's g of n? And then prove it. Pause the video right now. Do that. Once you've given it a shot, okay, once you think you have an answer for, again, your two constants, then resume the video again and you can check your work. All right, I'm going to assume that you did it. If you didn't try it, really, do it now. Okay, I'm going to give you the benefit of the doubt and assume you did it, right? Because if you didn't, you're just going to hurt your learning. Just looking at these isn't going to help you as much as trying them yourself. Right. But let's see what we got here. So we have n plus sine of n is big O of what? Well, let's see what's happening here. So as n gets big, this, n is growing bigger and bigger. But sine of n, that's just sine wave, right? So if we were to graph this, what we're really seeing here is, so n is just the diagonal, and we have this guy kind of like going, oscillating around this diagonal here. So it's big O of n. N is the dominant term. N is growing a lot faster than sine of n, which is effectively constant, right? So g of n is going to be n once again. All right. So let's see. So how did we prove this then? So we want to say that f of n is less than or equal to some multiple of n, all right, for all n that's at least what point, okay? So what'd you use for this, right? My guess is that a lot of you use 2, and I think that's actually a pretty good choice here, right? Well, if it's 2, then what would you use here? So let's see. If I subtract n from each side, so sine of n less than or equal to n, is that always true? Well, let's see. Certainly the sine, okay, always oscillates. So I know that the sine of n is less than or equal to 1 all the time, right? So therefore the sine of n, okay, is less than or equal to 1, is certainly less than or equal to n, as long as n is at least 1. Okay, there's my n naught. Okay, c equals 2, n naught equals 1, done. Okay, great. Okay, you can try different things. There are different examples, just like on the last one. There are different examples that work here, but this is a pretty easy one to show. Right? Now that's big O. Now, if we start to look ahead here, we see that big O isn't the only asymptotic. There's also these other ones. And so first of all, you might even wonder, why do we care about other ones? All right, well, let's go back to our example here with f of n equals 4n plus 15. All right, now no one said this, probably, but what if I had used g of n equals n squared? Okay, now I know that feels weird because, 4n plus 15 is big O of n, but the question is it big O of n squared? Well, let's use the definition and figure that out. Can I say that 4n plus 15 is less than or equal to some multiple of n squared eventually? So for all n bigger than or equal to some constant? Well, sure. I mean, in fact, right? Let's pick something super simple here. I could pick a 19 here, and again, 4n plus 15 is less than or equal to 4n squared plus 15n squared, which equals 19n squared. Okay. When is that true? Well, certainly when n is bigger than 1, or at least 1. So c equals 19, n equals 1. So basically this, or n not equals 1, basically the same solution that we had for the other case over here. Huh. So 4n plus 15 is big O of n squared. How about, could I say 4n plus 15 is big O of n cubed? Sure. Okay, just plug in an n cubed here and work through the same thing, and you're going to find that it's true. Could I find that 4n plus 15 is big O of 2 to the n? Yeah, pretty much everything is big O of 2 to the n, right? 2 to the n grows so fast that, the inequality is going to be true kind of really no matter what, right? So it seems like big O isn't necessarily as useful as it could be, right? Well, we have cases for that, and there's reasons why we use big O. We use big O when we're sure that it's less than or equal to some, but maybe we're not even sure if there's a tighter bound on it. So let's go ahead and introduce some others. So here's big O. We have our definition here. Big O gives an upper bound, right? So since it's less than or equal to, it gives an upper bound on how fast this function grows. Okay. You can also go in the other direction. So we're going to say that f of n is big omega of g of n if f of n is greater than or equal to c times g of n eventually. Okay, big omega gives a lower bound, right? So it's like you're saying that this function is no smaller than a multiple of this other function. Okay. And we're going to use that sometimes when we do actually what are called lower bound proofs, right? And we'll do one later in this course. When you're answering question 7b, you do not need to write over the whole thing. You notice that they are identical definitions with the exception of the direction of the inequality. Okay, so it's going to be the same thing. Right, and again, I could think about this as being like, here's my f of n function. Here's my multiple of, c of g of n, right? So that's sort of like my big O, and maybe if I were doing the big omega, maybe I have some other constant here that's times g of n is we're going to find that our function is always bigger than this constant of multiple of g of n. Okay. All right. Now, if both these things are true, right? So our function is sandwiched in between two different multiples of the same function. Then we have a third one right here that is called big theta. F of n is big theta of g of n if it's both big O of g of n and big omega of g of n, right? Or equivalently, you could write out both definitions and sandwich it together here. So it's big theta of g of n if f of n is bigger than one multiple of g of n and less than another multiple of g of n, again, eventually. Okay. Now that turns out to be a much tighter bound. Big theta is really, when you first learned big O and you thought about the intuitions behind big O, I'll tell you what, your instructor is probably lying to you. It wasn't big O that you were really building intuition about. You're actually building intuition about big theta. Whoa, everything that I've learned is a lie. Yes, that's true. Okay, but it all transfers over directly to big theta, so you don't have to worry about that. All right. So that's decent, right? So let's take a look at some examples here, right? So question 10, go ahead and well, actually, before we hit question 10, let's review a couple first. So true or false, and these are the kind of things that show up on exams, right? Where instructors like me try to get you with these. Again, we're just trying to get it and make sure you understand what's going on here. 3n plus 2 is big O of n cubed. All right, and again, you have to ask yourself, is 3n plus 2, is it a less than or equal to some multiple times n cubed? And the answer is yes, right? And it's not a very tight bound, but it is a true statement, okay? So that's true, okay? Is it big theta of n cubed? Well, let's think about this here. Is 3n plus 2, again, go into the definition of big theta, it has to be sandwiched in between multiples of n cubed, okay? Different multiples, right? So is it less than or equal to this guy? Sure, I could throw in a 5 here and it would all work out, and I could show it with a little bit of algebra. But how about this guy? Is there any multiple of n cubed that's when n gets big, where n cubed is going to be less than or equal to 3n plus 2? No way, right? This part right here is not true, okay? So it is 3n plus 2 is not big theta of n cubed, okay? So like that. All right, sounds good. So we got those guys. We just worked those through. That's good. What I want you to do is go ahead and do the same thing on your quiz right now. So question 10, go ahead and answer those now. Okay, assuming you did. What do you have for A? That's right, you had true, right? So it's big O. What do you have for B? That's also true, right? Very similar to the couple that we just looked at here. What about C? Oh, C is not so much, right? So C is false, right? So very similar to the ones that we did here. Okay. So let's talk a little bit about the uses of these things, right? So by definition, we apply these to functions, right? Big O of, f of n is big O of g of n, and we're talking about actual functions here. So this function is big theta or big O of another function g of n, right? That's by definition. In practice, we generally apply it to algorithms, right? Talking about running time, right? So f of n, right, is maybe, it's the number of executions of that most executed line of code, right? How many times are comparisons being made in a sorting algorithm, right? Where n is the size of the array that you're sorting, or something like that. In that case, then we say things like the fact that selection sort is big theta of n squared. Okay, selection sort is an n squared algorithm, or is a quadratic algorithm. Those all mean equivalently the same thing, right? But also, it's also the case that that big O can talk about can be applied to a problem, right? So here we're talking about the complexity of the problem, how hard it is, and for that problem, you're talking about the running time of the best algorithm that solves it, right? So we could say something that the problem of sorting is big O of n squared, all right? And that's true, and you might even think here, well, wait a minute, I know of a sorting algorithm that's faster than this. It's actually, I know of merge sort, and that's n log n. Sure, and that is still big O of n squared. So I can still say this safely, right? I couldn't say that the sorting problem is big theta of n squared, right? Because the best algorithm is not n squared. All right, but that's a little bit of context. We'll come back to that when we look at a problem tomorrow. Okay, now let's talk a little bit more about big O and about style. Again, you're doing exam questions here, and you want to know sort of what's legit and not. So I can say that 3n plus 2 is big O of n cubed. It's not quite as useful as saying that it's big O of n, right? In fact, I have a bunch of problems. Maybe it has a bunch of loops, and I have running times, that are like this, and maybe I have another one that's maybe a triply nested loop, and it has runtime that maybe looks like that. And if I asked for the big O runtimes on these, you can imagine a student that says, oh, that's big O of 2 to the n, big O of 2 to the n, big O of 2 to the n, and just doesn't even think about what they see here. They're just kind of a smart aleck, right? Yeah, technically they're correct, but again, not that useful. So on tests, when I ask stuff about running time, I'm generally gonna constrain you a little bit more so that you're not gonna be able to get away with that. I'll ask you, what is the big theta running time? And then you'll have to say things like that's n, and the second guy is n squared, and this third guy, theta, is n cubed, right? So anyway, just to let you know. The other thing is that, g of n, technically by the definition, g of n doesn't have to be very simple, right? So this statement is technically correct, but if I'm asking you, 3n plus 2 is a big O of what, right? It's a lot easier to write n for you, and it's a lot more useful because n is easier to parse than to try to think about this whole statement here on the right. So I would say that if you were to write something like that, it would be very much in poor taste. And you might make your grader in a bad mood, and if your grader's in a bad mood, they might actually take off some extra points or something, even though your answer were technically correct. So please, when you think of you're picking your g of n to use, pick something that's simple, right? Simple as possible. That'd be great. All right, one final thought here is that when we're talking about big O and runtime, there are times that you might actually choose a higher order algorithm, maybe a quadratic algorithm, over a lower order one, like a linear algorithm, right? And you might think, well, that's kind of weird. I thought we really care about efficiency. We want things to be as fast as possible. And yes, that is true. But again, let's look at the bigger picture here. Do you always want a faster algorithm? Are there any other issues that you should consider, any other trade-offs that you'd have to make, and so on? And what I want you to do is to brainstorm some ideas, right, on the quiz. What I'm going to have you do is in class, we're going to ask you to share the ideas that you have. So we're going to be calling on people to share the ideas that they have, and we'll see how you did. So take a minute right now and brainstorm some of those ideas, and you'll be able to go over them in class. Okay. And I will mention one just to get you started, is that sometimes if you got to remember that this is in the context of software engineering, that sometimes what you want to start with is a simple, easy to understand algorithm. It's going to be faster to write, so maybe you're not going to be executing it that often, and you don't really care how long, if I'm just running it a couple times, maybe I don't care if it runs a little bit longer, right? We're not talking about Google search now. We're talking about some little tool that you're developing that you're just trying to, gather a little bit of data and experiment, right? So if it's easier code to write, then it might actually, if it's faster to write, then that's more important than being faster to run, right? Simpler code is also easier to debug. It's easier to understand. It's easier to maintain. So sort of some software engineering concerns here, right, that we care about. So for instance, maintainability, and even, like just the general correctness of the code, right? And along those lines, I'll leave you with a quote here. So the inventor of quicksort, so C.I.R. Hoare, wrote, "Premature optimization is the root of all evil," right? And that's in some sense, that's kind of a stronger statement even than what the Bible says about the love of money, being the root of all kinds of evil. But here he says premature optimization is the root of all evil. Notice he does not say that optimization is evil. There's nothing wrong with optimizing your code, right? Very important adjectives here. Premature optimization, right? So if you start off trying to write something that's crazy complicated just to make it a little bit faster, you're probably better off starting with something simpler that you can understand, that you can make sure works, and then go back and try to cut some runtime off your code by changing your algorithm up a little bit. Tomorrow we'll take a look at an example of an algorithm. We're going to look at actually 3 different implementations of that algorithm, starting with simpler ones and then going to more complex ones. All right. Go ahead and finish your quiz, and that's it for today. We'll see you back for next class.